What specific problem does Intern S1 aim to solve in the context of scientific research, and how does it differ from existing open-source models?
Intern S1 aims to bridge the significant gap in scientific understanding and reasoning capabilities between open-source and closed-source models, particularly in low-resource scientific domains where existing models struggle. Unlike current open-source models that primarily excel in popular domains like mathematics and code, Intern S1 is specifically designed to handle complex scientific tasks by processing diverse modalities including images, text, and scientific data. It employs advanced data curation strategies, such as a recall and filtering pipeline that enhances the purity of scientific data from around 2% to over 50%, and a dynamic tokenizer that improves efficiency in encoding scientific strings. Furthermore, Intern S1 integrates a mixture of reward framework for reinforcement learning, allowing it to learn from a wide array of tasks simultaneously, which enhances its adaptability and performance in scientific reasoning. This comprehensive approach positions Intern S1 as a state-of-the-art open-source model that competes with leading closed-source systems in scientific reasoning benchmarks.
How does the proposed method or algorithm of Intern S1 work? Please illustrate its operation step by step, particularly focusing on the pre-training and reinforcement learning phases.
The proposed method of Intern S1 operates through a structured approach involving pre-training and reinforcement learning, RL phases. In the pre-training phase, Intern S1 utilizes two data curation pipelines, one for mining high-quality scientific data from web sources, enhancing data purity from 2% to over 50%, and another for parsing PDF documents to extract scientific knowledge. This results in over 2.5 trillion tokens of scientific data, which is then used for continued pre-training, Captain, in a large-scale interactive environment called Intern Bootcamp, employing a mixture of reward-more framework to harmonize diverse feedback from various tasks into a unified reward scalar. In the reinforcement learning phase, Intern S1 first conducts offline RL using meticulously curated instruction data, where responses are generated through best-of-n sampling to ensure quality. Following this, the model undergoes online RL, where it learns from over 1,000 tasks simultaneously, employing a hybrid offline-online data filtering strategy to balance performance across tasks and prevent overfitting. This comprehensive approach allows Intern S1 to achieve state-of-the-art performance in scientific reasoning while maintaining adaptability and efficiency across diverse tasks.
Can you provide a simple yet illustrative example demonstrating the inner workings of Intern S1, particularly how the dynamic tokenizer processes scientific data?
The dynamic tokenizer in Intern S1 processes scientific data by first identifying the specific modality of the input string, such as molecular formulas or protein sequences, and then applying tailored splitting strategies for each identified modality. For instance, when encountering a smiles representation like less than smiles greater than C1 CCCCC1 less than smiles greater than the tokenizer recognizes it as a molecular structure and uses a specialized splitting method that optimally compresses the data, unlike a static tokenizer that applies a uniform strategy across all types. This approach allows for higher compression ratios, improving efficiency by up to 70% compared to other models like OpenAI's GPT-OSS120B. Additionally, the tokenizer employs heuristic rules and domain-specific tools to automatically detect and tag scientific strings, ensuring that each modality is processed accurately and effectively. By concatenating the resulting sequences into a single input, the dynamic tokenizer maintains compatibility with modern large language model architectures, enhancing the model's overall understanding of scientific modalities.
What are the key theoretical or practical benefits of using the mixture of reward-more framework, and how does it enhance the performance of Intern S1 compared to traditional methods?
The mixture of reward-more framework enhances the performance of Intern S1 by integrating diverse reward signals from multiple multimodal tasks, allowing the model to acquire both domain-specialized and general-purpose capabilities within a unified optimization process. This approach contrasts with traditional methods that optimize for individual capabilities in isolation, which can lead to suboptimal performance across tasks. More harmonizes feedback from various task types, such as logical reasoning and instruction following, enabling the model to maintain high performance on specialized tasks while ensuring robustness in open-ended dialogue scenarios. Additionally, the framework's flexibility in handling different task difficulties and convergence speeds through a hybrid offline-online data filtering strategy improves overall training efficiency. As a result, Intern S1 achieves state-of-the-art performance among open-source models and competes effectively with leading closed-source systems, demonstrating the practical benefits of the More framework in enhancing model capabilities.
How is the effectiveness of Intern S1 validated through experimentation? Discuss the datasets used, benchmarks applied, and how results demonstrate the model's performance compared to existing systems.
The effectiveness of Intern S1 is validated through extensive experimentation across a variety of benchmarks that encompass both general and scientific reasoning tasks. The model is evaluated using influential datasets such as MMLU Pro, GPQA, AMY 2025, and several scientific reasoning benchmarks like ChemBench and MathBench, which cover core disciplines including mathematics, physics, and chemistry. Results indicate that Intern S1 achieves state-of-the-art performance on multiple benchmarks, outperforming previous open-source models by significant margins, such as +257 on MathBench compared to Intern VL 3-78b. Additionally, on multimodal scientific benchmarks, Intern S1 ranks first on 4 out of 5 datasets, demonstrating its competitive edge against leading closed-source models. Overall, these results highlight Intern S1's capability to narrow the performance gap with closed-source systems, establishing it as a leading open-source multimodal scientific reasoning model.
What limitations or challenges does Intern S1 face in terms of scalability, generalizability, or computational resources, particularly regarding its architecture and training processes?
Intern S1 faces several limitations and challenges related to scalability, generalizability, and computational resources, particularly in its architecture and training processes. One significant challenge is the reliance on high-quality, domain-specific data for pre-training, which is difficult to scale across low-resource scientific domains, as evidenced by the need for extensive data curation pipelines that enhance data purity from 2% to over 50%. Additionally, the model's architecture, which employs a mixture of expert mode design, introduces complexities in training due to the dynamic routing of experts, leading to potential discrepancies between training and inference phases that can destabilize the learning process. Furthermore, the training infrastructure requires substantial computational resources as it utilizes advanced techniques like fully sharded data parallelism, FSDP, and FP8 precision, which can be resource-intensive and may limit accessibility for broader applications. Lastly, while the model shows strong performance in scientific reasoning, its generalizability across diverse domains remains a challenge, as it may not perform uniformly well in less represented areas compared to more popular domains.